Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the lecture 14 Bipolar Junction Transistor part 3 and welcome to the course E207 Electronic Devices and Circuits. So we have been discussing BJT since last two lectures, so we will carry forward that. My name is Deepak Jain, I am an assistant professor at Electrical Engineering Department of IIT Bombay. So this is the course content. So for this particular lecture, we will talk about the non-uniform doping in the base region. In the last lecture, if you remember, we talked about the static characteristics of these minority charge carriers in different region, base, emitter and collector. So now we will deal with the case where in the situation wherein in the non-uniform doping is there in the base. Like in that analysis in the previous lecture we assumed a uniform doping. So today we will see the situation where there is a non-uniform doping and what are the consequences of that. Other than that, we will talk about basically different configuration, like we discussed about the common base configuration mostly in the previous lecture. We will talk about the common emitter and common collector, as these transistors have three terminals, so any one of them can be made common, and we will see what impact it brings in terms of application and the characteristics, etc. We will also talk about narrow base width, under what circumstances the effective base widths get narrow, and this effect is known as the early effect. Then we will talk about avalanche breakdown. We discussed that avalanche and Zener breakdown in context of PN junction diode, and as we know in NPN or PNPN transistors, the second junction is reverse bias. So one can ask, will avalanche breakdown happen here or not? And in last we will talk about the thermal effects. Okay. So what are the right conditions to operate the transistor and what the impact of heat on the parameters of the transistors. So let's talk about the first non-uniform doping in the base region. So far let's say this is our PNP transistor, emitter, base and collector. So far in the previous lecture we assumed the doping profile in this region, and in this region is uniform. So today we are going to discuss what will happen if this is non-uniform and why we are discussing that. Let's see it from the fabrication perspective. Let's say you have a p-type substrate and you do a n-type doping. This is n-type doping for base, and then there is again p plus doping, which is emitter, base and collector. Of course there will be metallic contacts, etc. Now what happens, let's say Na is the doping concentration for this p-type substrate, which is sort of a background doping for both of these n-type and p plus type region, emitter and the base. So if I draw this, so this doping profile for the background substrate is something like this, and because of the doping of this, let's say donor ions in this n-type base region, the profile would look like something like this, let's say. So in this region, this is not uniform, right? And similarly for this, it can go something like this. Okay, so this is Na, this is Nd, this is Na already. This is, let us say, X or whatever parameter you want to say, and this is your doping concentration. So this non-uniformity is due to the fabrication challenges. It might not be that easy to have a perfect uniform. So that's why it is important to discuss like what this non-uniform doping profile brings to the transistors. So let's first see the case, what happens, forget let's say transistor, what happens when there is a non-uniform doping, what will be the consequence of that. So let's say we have a n-type semiconductor where the doping profile is something like this. Something like that, which is exponentially decaying or whatever. So there is a gradient. So if I basically try to draw the charge distribution, it will look like something like this. Since donor ions are there, they have free electrons, so donor ions have a positive charge because they are giving the electron. And since concentration gradient is there in this direction, so it will look like something like that. So because of the concentration gradient, electrons would like to move in this direction. If you remember, we talked about diffusion current, right? So because of the concentration gradient, so electron would like to move in this direction due to concentration gradient. But as soon as electrons will start moving here, there will be a charge distribution, positive charge and negative charge, right? And there will be electric field in this direction. So movement of electrons from here to here will lead to the formation of electric field in this direction. And because of electric field is in this direction, it will pull back electrons. Electrons would like to move here, move in this direction due to electric field force, Coulomb force, right? So because of electric field movement is happening, current is being formed. So this moment you can say because of this electric field, and current will form in this direction because electrons are moving in this direction. So current direction would be here for drift 1, and for diffusion current direction can be in this one. The movement is taking place the other way around, electrons are moving here in this case and they are moving here in this case. So under thermal equilibrium situation, like when there is no external applied field and all that, there will be an equilibrium where both the current would be equal and opposite to each other, and net current would be 0. But there is a built-in electric field. So the consequence of concentration gradient is that concentration gradient that leads to the formation of inbuilt electric field. But because of this equilibrium between drift and diffusion, the net current is 0. Okay. So let's see how we can derive the expression for the electric field in this case. So the expression for current would be a combination of drift and diffusion, and we know drift current, how to write that, QA basically, and diffusion coefficient, mu, then your mobility basically, and then your concentration gradient and electric field. So this is the drift current, plus now we'll be writing the diffusion current. So which comes out to be QA dN derivative of this concentration gradient with respect to x. Okay. So this is the expression for diffusion current, this is the expression for drift current, drift and diffusion. due to concentration gradient, and this is due to electric field. So, no external field is there just because there is a concentration gradient. Electrons would like to move in this direction, but their donor ions would like to pull them back. This leads to the formation of internal electric field, inbuilt electric field, and an equilibrium is achieved between this drift and diffusion. And this current, as I said, I should be equal to 0. Okay. So, now let us see what is the expression we get for the electric field after making this current to be 0. Let me rewrite this I is equal to QA mu n, which is mobility nx Ex plus QA dn, derivative of this nx with respect to x, which is equal to 0. Okay. So, now making it 0, it is fairly simple. You can eliminate QA. So, Ex comes out to be minus dn divided by mu n into 1 by nx derivative of this nx. Okay. And if you can recall the previous lectures, we talked about this expression. This is constant, dn by mu n is equal to kT by q, Einstein's relation, basically very simple, straightforward. If we just plug in it here, the expression for electric fields comes out to be minus kT by q divided by 1 by nx into double derivative of this. Okay. So, now this is the expression for the electric field, which depends, you can see, only on this doping profile, right. If this is 0, let us say there is a no gradient, it will be 0. So, the source of this electric field, source of this inbuilt electric field is just this gradient. If this gradient is 0, there will be no electric field, and if gradient is there, then there will be an electric field. Now, the good question is that can this electric field be constant? Can we design this doping profile in such a way that this becomes constant? So, it seems so from mathematical equation, or you can do some reverse engineering to find out that. So, what will be that expression? So, you can think about, and let me just write down that expression for you. That expressions come out to be nx, let us say at x is equal to 0, and not I have defined something like n at xn equal to 0, e exponential raised to power minus a divided by xn divided by base width, okay, width of the base region. Now, a is equal to log n n0 divided by log np. So, log of the concentration at x is equal to 0 and at x is equal to omega b, whatever values are there here, just ratio of that. So, if we plug in that into this expression what we just got in the previous slide, this expression. So, let me rewrite this expression here. It comes out to minus kT by q multiplied by 1 by nx and derivative of this nx divided by dx. If we just plug in this expression here, let us see what we get. One by nx into derivative with respect to x and not e raised to power minus exn by vb. So, what we get is minus kT by q, and not whole expression will come out minus a by vb if you just take a derivative of this, right. So, now minus minus will settle down and the expression we get is kT by q multiplied by a by vb, because this is already nx, right. Nx is this is how we have defined nx. So, sorry, Xn. So the expression for Ex, what we get is Kt by Q into A by W subscript B. So this is constant. So if we design properly the doping profile, we can get a constant electric field. Okay, that's the beauty. And of course, you can get different expressions based on this doping profile. So it's a doping profile which is creating, or which is the source of this inbuilt electric field. So now, since we discussed a generalized case, like what will happen when we have this grading in general in any semiconductor. So in context of PNP transistor or NPN transistor, so let's consider the case of PNP transistor. And let's say if we have this gradient, concentration gradient. So electric field will, this electric field will help the holes to cruise through this base, right? Because holes are supposed to pass through this base from emitter. Emitter is emitting holes, if let's consider the case of PNP. So this additional built-in electric field will let them cruise. It will aid this process. So that is good. So this shortening of this transient time from emitter to collector is very useful for high frequency applications. So you can say this inbuilt electric field shortens the transient time for holes from emitter to collector. And this is very good. So another approach other than this doping, what we discussed, is to engineer out the alloy composition basically. Then you can also get this inbuilt electric field. So you need to keep in mind when you discuss about transistor, so when you do any analysis, what's the doping profile? Is it uniform? It is non-uniform. If it is non-uniform, a lot of other things will come into the picture. So I hope you could understand what's the role of this non-uniformity here. So now we will move to the next topic of this lecture, different configurations. So far we discussed common base configuration, now we are going to discuss common emitter and common collector configurations. So since this BJT or bipolar junction transistor is a 3-terminal device, right? It has 3 things: emitter, base, collector. 3 terminal. So in first case we made this base to be common and we were applying voltages here and making these junctions forward and reverse bias. So we can also make emitter to be common or collector to be common, right, which is a very obvious question. So we have already discussed the case of common base configuration, in which base is common. In common emitter would be common, and common collector would be common. So now I will discuss the case of common emitter configuration. Actually, the reason to study this is that common emitter is more useful than the common base. So most of the time it's a common emitter configuration which is used heavily in case of transistors. So let's say this is my PNP. Okay, so what will happen? This is emitter, so this is common. Okay, this is base and this is my collector. So in this common emitter configuration, same base emitter junction, is forward biased, and your base collector junction is, or collector base junction is, your reverse biased. You can say collector base junction is your reverse bias. So, let us see what happens. So, base is here, this junction is forward bias, base to emitter is the forward bias. So, this has to be connected to a negative terminal, and this will be connected to this one, and since this has to be reverse bias, so this will be connected with the negative terminal, and this is already connected to the base. So, this is a common emitter configuration. So, if you want to draw the collector current, it is IC. If you want to draw the base current, it is IB, and this comes out to be IE. So, IE is equal to IB plus IC. Okay. So, this law will remain valid here. So, similarly for NPN case, you can draw the common emitter configuration if you want. So, let me do that. This is collector, this is base, this is emitter, this is short circuited, and since this is forward biased, so this will be, this is positive, this has to be connected to the negative, so this has to be positive. This is the common emitter configuration for NPN case, and this is for the PNP case. So, the only difference is that emitter is common here, rest is same. So, what are the applications? So, these can be used for voltage, current and power amplification again. Voltage, power and current amplification as similar to the common base configuration. And now I will draw the common emitter configuration, which is very obvious from here, like collector will be common as emitter is common in this case, and common collector configuration is not that popular. It has high input impedance and low output impedance, unlike these common base and common emitter, which has high low input resistance, input impedance and high output impedance. So, common collector, because of these characteristics, are being used in buffer circuits, circuits between two circuits for buffering basically. So, we are not going to discuss the common collectors in the detail. Of course, I will draw the diagram for the configuration, and then we will move to the common collectors and discuss their IV characteristics, etc. So, if I just draw it again, so let us say this is my collector. So, this is emitter, this is base and this is common. I am considering the case of P and P. Okay. So, here this is going to be connected with the negative terminal, with the positive terminal, and this is going to be connected with the positive terminal and then terminal. Right. And IE current will be here IB current will be here and IC is here. So this law IE is equal to IB plus IC will remain valid here as well. So why it is high input impedance? Because input is here between N and P, between base and collector, and we know that because of the biasing the input the impedance would be higher. So that's the common collector and may not be very useful. So we'll now move to the common emitter case and we'll discuss its input characteristics between I and V, and then we will discuss about its output characteristics both. And there's a very interesting phenomena known as the early effect which is associated, and this is what we will learn here. So common emitter configuration. So let me draw the input IV characteristics here first. This is V, this is IB, base current here. Here we are not talking in terms of your emitter current. Here is the base current because this is a common emitter configuration, and this voltage is your BE. So it's a forward bias junction, as we know in case of a common emitter. So this will be something like this. For a, let's say, some VCE, collector to emitter voltage to be 1 volt. This is a standard forward biased PN junction diode kind of IV characteristics, which is obvious. But there is a different thing. If you increase the VC, reverse bias voltage, what you get here in terms is something like this. So this is more higher VC, let's say, right? So this curve is shifting in this direction, which is very important. So to have a same base current, at different VCE, so we need higher base to emitter voltage if your voltage between VCE is higher. So this is the other way around. If you remember the case of common base where they were shifting in this direction. So there is a reason for that, why for same base current, at higher VCE, one would need higher VBE. Okay, so that's the thing we need to dig out. So now let's look at the output characteristics. This is input characteristics. Another important thing is that here IB is in microampere. So we need to keep in mind that the base current is fairly small compared to the IE, which is usually in milliamperes. Okay, so let me now draw the output characteristics. Let's see what happens in that situation. So let's consider the case where my base current is 0, IB is equal to 0. The curve of this, your IC versus VCE, will look like something like this. So even when base current is 0, some IC current will be there. Okay. This is unlike to a common base configuration where there is a IE is 0, the IC is nearly 0, but here it is significant. And another important thing, let me write down this point, that when IB is 0, IC is not equal to 0. And this is the one observation we had from this curve, that for same base current at higher VCE, one would need higher VBE, though small, but still it is higher. And here coming back to this output characteristics, what we observe is these IC versus VC curves for different IBs are not linear as this was the case for, okay, they are not linear. So with increase in VCE, IC is increasing. So the curve between IC versus VCE are not linear. Okay, so these three observations we have made from the input and output characteristics of the common emitter configuration. So something is different, definitely something is different from the common base configuration here, and that we need to dig out what is that. If we can dig out that and we can understand that physics, then we would be able to give the reasons for this. Okay. So before we do that, let's do some current equations for this common emitter configuration. So let's define alpha is equal to IC by IE. Okay. Now if I just want to write IC is equal to alpha IE plus ICBO, which is the reverse saturation current. Okay. And we know that IE is equal to sum of IC plus IB. Plugging that equation back here, what we get is IC alpha IC plus IB plus ICBO. Okay. And if we just do a very simple mathematics and if we derive the expression for IC, what we will get is alpha 1 minus alpha IB plus ICBO 1 minus alpha. This is the expression for your IC. Now let's discuss the first case of the output characteristics when IB is 0, right? Still IC will be ICBO divided by 1 minus alpha. And this alpha, let's say fairly close to 1, so this term can be significantly higher. Let's say if alpha is 0.99, this term would be ICBO divided by 0.01, and this number can be significantly higher. So IC can be higher. So this explains why when IB is equal to 0, there is some significant IC current is there, which is not the case in a common base configuration. So now here we can define IC is equal to beta IB plus ICO. So this is the current when your base current is 0. So this is the current you are going to have, and beta is your amplification factor, alpha minus 1 minus alpha. Okay, so beta can loosely be defined as IC divided by IB. Okay, so beta is a very important factor when it comes to the common emitter configuration, and this decides a lot. Now this gives some mathematical understanding of this, why this is there, but we do have some other observations like why these curves are not linear, why this is shifting this way. So let's discuss those things into the detail based on the bandwidth modulation, base width modulation. So base width modulation, which is also known as the early effect. So what happens, let's say we have a PNP transistor. When you apply this reverse bias between these two terminals. So we know from the very basics of the semiconductor physics, and this is what we discussed in the beginning of this course, that this let us say this is P plus region. So, depletion width will penetrate more here because of this space charge neutrality, right. Q, A and D equal to Q, A, area is assuming same, N, A into your X in this direction and X in this direction. So, here ND is small, so XD has to be much larger because NA here is much larger. So, XA would be much smaller. So, this is the case, right. So, already this width will be higher here compared to here, and on the top of applied battery, this will further increase this depletion region, this will add to the V naught. Okay. So, because of this equation and because of this doping profile reason that base is lightly doped compared to this collector, this depletion region will be more and more inside the base region. So, you can have something like this. This is, let us say, so something like this you can have. Okay. So, let us say my entire initial length was WB and this length now becomes L. So, the effective base width is WB by minus L. So, it has important consequences, this phenomena, and this is known as the base width modulation. So, basically what will happen now, holes, let us say if you are considering a case of PNP transistor, holes have to transit less distance, right, before reaching to the collector. So, when Vc is increasing, so what will happen? What will happen here? Because it has to travel the less distance when IE is going on with increase in Vc. So, when Vc is increasing, your L is increasing, this distance L, and your Vb minus L is decreasing, and if this is decreasing, then IE will increase, which IC will increase, sorry, because the emitter has to travel the less distance. So, most of the emitter current will be able to reach to the IC. So, ICP will increase. So, that is why you see these characteristics, that when you increase VCE, your IC current for different IB is increasing. Okay. Because of this, as Vc is increasing, your depletion length is increasing, your base length is decreasing, which is increasing your IC current, because now most of the current is able to increase, reach to the collector region. There is a very less recombination compared to the situation where this was a significantly large. So, this basically explains why these curves are not linear. So, now we have answer for this question. We also would like to know what is happening here, that why for same base current at higher VCE we would need higher VB. So, now we know that, right, base current is going down, with base current is going down here because less thin region is there. So, less number of electrons would be there to constitute the base current. So, base current is going down with increase in VCE. So, in order to maintain the base current, we would need a higher VBE to compensate the effect, right. We would need more voltage to increase the base current. So, that is why you have this curves like this way. Okay. So, I hope this base width modulation or early effect explains the whole dynamics, why these curves looks like this. So, this should be taken into account while we discuss these IV characteristics of this common emitter configuration. Now, another interesting thing that one can ask, like if we keep increasing this VCE, what will happen? Will it be completely depleted? Is it possible that this region is completely depleted and then all the emitter current will reach to the IC, right? Transistor won't work in that situation. Answer is yes, it is possible. That and this is known as the punch through process. Punch through process, and this is possible. So in this case, entire base width is depleted, but before this punch through process comes into the picture, something avalanche breakdown happens. And if you remember, while discussing this PN junction diode, we talked about this Zener breakdown and avalanche breakdown. Zener diode requires special doping profile and all that. So you can ask, like, if we are already increasing this voltage to that high level, then avalanche should come into the picture. And answer is that yes. So before punch through happens, this avalanche breakdown comes into the picture. So we will now talk about that avalanche breakdown for both common base and common emitter configuration. So let me draw that. So first for the common base configuration, and then we'll talk about common emitter configuration. Okay, so in common base configuration, VCB, your IC is there. So these curves are like something like this. So if you talk about this region, so this is the breakdown region, breakdown voltage, at which this IC current starts increasing dramatically, right? And you see an avalanche breakdown basically. So this is a fairly sharp voltage you can see here, and this is a case of common base. Now let's talk about the case of common emitter. What happens? Here we have IC and VCE, and so here you can see the situation where IB is equal to 0, IC is there, here the situation where I is equal to 0, and these are different IEs. And here your IBs are different. So you can see that this breakdown region here is not sharp, fairly broad. Unlike here, where there is a very sharp breakdown voltage at which this is happening. And another interesting thing that you should keep in mind, this is much larger. So this breakdown voltage here, which is VCEB, so VCB is larger than the VCEB. So breakdown voltage is larger in case of common base configuration. Second thing is that in common base there is a sharp breakdown voltage, avalanche breakdown voltage. On the contrary, in common emitter this breakdown voltage is fairly broad. Okay, so that's the basically difference. So breakdown voltage is significantly smaller and there it is very sharp. So you can see that in common emitter case there is a strong influence of the carrier multiplication, charge carriers multiplication over a fairly broad range of the collector voltage. So multiplication effect is there, carrier multiplication effect is there. Over a broad range of voltage. So let's quickly see mathematically what is going on. So if I write down the equation for the current here, IC is equal to alpha IE plus ICEO. This is what we have discussed. Now what will happen because of this multiplication, avalanche multiplication, current will increase dramatically. So it can be written as alpha IE plus ICEO multiplied by a factor of m. Okay, and what is m, right? M can be written as 1 minus applied voltage divided by the breakdown voltage, whatever it is, between CEB or whatever junction it is, raised to power n. So basically there, as you know, this is what we already discussed, this avalanche multiplication in past, that one electron creates another electron hole pairs and generated electron will create another electron hole pair. So this multiplication keeps going. So of course these n would depend on the type of material that have been used, but it multiplies this way. And this probability of ionization increases with increasing electric field. Therefore, to depend on this reverse bias, like voltage plays a very important role. If voltage is higher, then more multiplication will happen in this reverse bias. And and this is what we have discussed in common emitter case, common base case. The explanation for this why this is higher and shorter, the value for the breakdown voltage is shorter compared to this common emitter configuration, is that when this electron hole pair generates, so in case of this base to collector region, so holes will drift quickly. Let's say we are considering the case of NP here to the collector region. So electron hole pair, let's say they have been generated, so electron will be here, but this electrons will remain into the base, these new generated electrons, and because of the space charge neutrality there will be more holes from the emitter region, and this will again increase the number of holes passing through, and then again this process will multiply and the current will increase exponentially. Okay, so I hope you could understand a bit about this avalanche multiplication. Now we'll talk about the thermal effects that what are the thermal effects in case of the transistors, and what are the impact, and how do we avoid these thermal effects and why should we avoid. So if the current IC is fairly large, let's say, so at the collector junction a significant heat can be generated, right, and it can lead to the heating of the device. Now, in particular this IC, the current, and this voltage VBC, V subscript BC and IC. So, multiplication of these two decides the power max basically. Okay. And this gives you the power being produced, and there is a maximum limit over which one can afford. And what decides this maximum limit, that is important. What happens when these electrons passes through this collector region, they say like electric field increases their kinetic energy and they go for the lattice scattering. So, lattice scattering is very important here. And if you remember in the beginning of the course, we talked a lot about this lattice scattering, and this heat dissipation, this lattice scattering leads to the increase in the temperature. Okay, these electrons have high kinetic energy, they undergo through this lattice scattering, and this leads to the heating of the device, or you can say higher temperature. Energy is being converted from kinetic energy to these heat. Okay. So, there are two ways, like if you want to increase the power handling capability of these transistors, that one can use the heat sink. Okay. This is very common, and heat sinks can dissipate the heat quickly. Air cooling, these kind of things are used for heat management, but it is not of course always effective. So, there are two consequences basically of these collisions and all that. Because of this temperature increase, your mobility will go down, right? Mobility will go down. If you remember the curve for temperature versus mobility, this was something like this. In the very beginning of the class, this course we studied about that. Okay. So, if mobility will go down, d by u kT by q, if mobility is going down, this diffusion will also go down to maintain the ratio. So, which is not good, because if d is going down, beta will go down, right? Amplification will not be there. But because of all these collisions and all that, the tau, this time period basically, lifetime period, tau p will increase, and this will increase beta. Tau p will increase beta, and this effect with respect to this lifetime is more dominating than this effect, more dominating. Okay. And this will further increase the IC, because we know that what is IC is equal to beta IB, right. So, a large amount of current will flow. Temperature is increasing, it is increasing the beta, and again current is increasing. So, it becomes a cycle. So, you can say like first IC is higher, which is increasing the temperature, which is increasing your tau, which is increasing your beta, and which is increasing your again current. It becomes a cycle, and it can dramatically increase. The temperature can IC can dramatically increase, and this increase in IC can lead to a situation of thermal runaway. So, that is not good, of course. So, the conclusion here is that we need to control the current, and we should know the P max IC into VCB, or you can say V whatever, depending on that. So, if I just summarize everything, so we discussed about the non-uniform doping. This non-uniform doping can lead to inbuilt electric field, which leads to the equilibrium, thermal equilibrium, net I current is 0, okay, net I current is 0, and this electric field depends on your doping profile, because only this doping profile gradient has created this electric field, okay, and for the right set of profile, this electric field can be constant as well. And how does it help? It helps in reducing the transient time. Reducing the transient time. So that's very important advantage of this non-uniform doping. Then we talked about different configurations, emitter, common emitter and common collector one. And afterwards we talked about narrow base width, which explains why IE versus VCE curves are not linear, right. So with increase in VCE, IC increases with respect to VCE for constant IB. Okay, and we also talked about avalanche breakdown in transistors. Why does it happen? Then we also talked about punch through process. And at last we discussed about the thermal effects. So I hope you got some idea about transistor, more insight of the transistors. In next lecture we'll discuss more. Have a good day. Thank you very much.